have a look at this diagram. Okay. Now this is what we were doing before with just establishing first principles, doing the whole rise over run thing. And what I said was you pick some x value, call it x, and you say, let's just go forward a bit. Let's call that bit h, and you got x plus h, right? And that's where our definition of first principles came from, right? Now it's one definition. It's not the only one. I'm going to show you another one which is not quite as popular, but it is extremely, extremely useful. In this case, I'm about to show you. Okay. So instead of saying x in some other place x plus h, right? I'm just going to call this other coordinate c for some constant. Okay. And that makes this distance here, this distance, x minus c. Do you agree with that? Like it's just that one minus that one. That's the difference. Okay. Now this is x, f of x. If this is c, then f of c. Very good. Okay. So just like I have run down here, I have rise here, which of course is exactly the same thing just with f's, right? The function evaluated at those points. Okay. Now because we have phrased things differently, I now have a different and alternative way to write first principles. I no longer have the limit as h approaches 0. For starters, because I don't have an h, right? What I really want is for c, this number, I want it to get closer to x, so that they sit on top of one another, so I have the tangent, not the secant, right? So instead of saying h approaches 0, I want c, now in some ways you can write them either way around, but hopefully as I finish this, you'll see why I want it this way. I want c to approach x. I mean, in some ways, c approaching x, x approaching c, they're going to end up on the same spot. Now, what's happening here with rise over run? Okay, here's rise, and here's run. So I have this. There's my dy, and there's my dx. Okay, now you're thinking, well, so what? Like, is it any better than the other? It's not at all obvious that this is actually very useful to us rather than the other form. Here's why I'm going to pull it out. You've been looking, and you've already, one more thing, noticed that this is our derivative of y, right? Where y is like x squared or x cubed, something like that, right? Can you see here that this is just change in y, change in x, right? But I can write this a slightly different way, like so. See that? I'm doing something to y, whether it's x squared or x cubed or whatever you like, okay? What I'm doing is finding the derivative. That's what this really means, right? We call this this process of finding the derivative is differentiating, right? Find the derivative or differentiate. It's not called deriving, please don't call it that. I'll throw a sharp balloon at you. It's called differentiating. So this is called the differential operator. When you put it on the front of something, it means whatever's there, you differentiate that, okay? There might be an x squared, or an x squared minus 1, or anything there. That just means differentiate it with respect to x. Now, you have noticed that if you differentiate x squared, okay, out pops 2x. If you differentiate x cubed, with this example as well, you get 3x squared. If you really want to go binomial, I can't remember if one of the questions does this. If you differentiate x to the power of 4, you get 4x cubed. Now tell me there's a pattern here, right? Clearly there must be a pattern I can take advantage of. Now the pattern I see is that you have something raised to a power, right? That power seems to drop out the front and become the coefficient, right? And the power itself reduces by 1. That's really at 2x to the 1. You see that? Okay. So I notice a pattern. That's good. But why should this be the case? Well, watch as we use this guy. Okay? What I want to differentiate is let f of x be x raised to some power, whatever power you like. Okay? I'm going to use first principles to show that this is the case. Okay? Okay. So, just according to this definition of, whoops, I rubbed this off. This definition of first principles, it's going to be, this is going to be f dash, the limit as c approaches x, because I want the tangent, not the secant, of, what's on the numerator? There's f of x, and there is f of c. Do you agree with that? Just put x and c into the appropriate spots. And I have x minus c on the denominator. Now, because I don't know what the power of n is, in its current state, I can't do anything. Okay? But if I did know what the power of n was, it'd be okay. For instance, if n were 2, it'd be this case, right? There'd be x squared minus c squared. So you'll have difference of squares, right? Then what would happen is, in this case here, it'd be, what am I going to get? I've got x's and c's instead of a's and b's, okay? So I'm going to get x minus c, x plus c, right? All over x minus c. You see my denominator? What's going to happen? Cancel, cancel. C is going to approach x, right? So that guy's going to become x, right? X plus x, which as we've already noticed, 2x, right? What about this guy? I'm going to get x minus c, x squared, cx, c squared. You've done this question in the quiz this morning. Did you notice I snuck it in?
Yeah.
On x minus c, right? Cancel, cancel. All of the c's are going to become x's. So you get x squared, x squared, x squared. You get 3x squared, just like you were expecting. Okay? Now you can satisfy yourself and expand out to the power of 4. But do you not see a pattern here? Do you not see a pattern? You're going to get an a minus b out the front. What will ensue? All of these things. This is kind of like a binomial expansion with none of those coefficients in there. Right? There's no 1, 3, 3, 1. There's no 1, 4, 6, 4, 1. It's just ones. Right? Does that make sense? So you can see it's going to be, what will the first term be?
N minus 1.
When I had 2's, this was a 1. Yeah, when this was a 3, this was a 2. When this was a 4, this was a 3. So here, instead of n, I'm going to have n minus 1. Yep. Okay. Then I'm going to have a to the n minus the next one is 1 down. N minus 2. And then a b. And then n minus 3, and then b squared. All the way until, what will the very last term be? Oh, I have no more a's. All the a's will be gone. B n minus 1. See the symmetry there? There and there. You got it? Okay. Now, watch. Look at this. Okay. I have x's and c's. Okay. So the limit as c approaches x of x minus c, this guy, right? X n minus 1, x n minus 2, x n minus 3, all the way until, what's my last term?
Bn
C,
oh, wait, hang on.
minus 1.
Okay.
Okay. All divided by the run, x minus c. There it is. Okay. Cancel, cancel. Okay. Now, hold on a second. All of these c's are going to become x's, right? Every single one. Just like this one and these ones, okay? So the first term you're going to have, bless you, is x to the n minus 1. Doesn't have any c's in it. When this c becomes an x, what will the whole thing be?
N minus 1.
X to the n minus 1, right?
Yeah.
And then when these c's turn into x's,
N minus 1.
it'll be x to the n minus 1. And then all the way, because that one, obviously, the c will turn into x. And you get this. Now I have a whole bunch of these things. How many of them do I have? I have n terms, right? Because watch. When it's a 2, I have 2 of them. When it's a 3, I have 3 of them. When it's a 4, I have 4 of them. When it's an n, I have n of them. N, x, n minus 1.
Yay!